Viewer discretion advised. This program contains detailed descriptions of industrial accidents and their technical causes. It examines deaths, systemic failures, and the effects on survivors and rescuers in a sober, factual manner. Unveiling shocking industrial disasters does not mean chasing gore or sensational headlines. It means tracing how routine work, simple assumptions, and thin safety margins combined to produce preventable catastrophe. Today we lay out 3 case studies: the furnace chamber deaths at Salzburger Aluminium AG in Lenzing, Austria on March 8, 2012, the deadly degreaser tank incident at Evernu Metal Products in July 1986, and 2 robot-related fatalities in the late 1970s and 1981, each a different technology, each a different scale, but all pointing to the same horrible truth. Systems meant to protect people can, under particular conditions of training, culture, design, and oversight, become instruments of death. If this subject matters to you, stay with us to the end. Subscribe for more investigative examinations of workplace safety, and if you have a story you think should be told, there's a way to submit it at the end of this video. On the morning of March 8, 2012, at a long-established aluminum plant in Lenzing, operated by Salzburger Aluminium AG, commonly known as SAG, 2 men entered a preheating furnace chamber to investigate a reported loose metal plate. The chamber was part of a furnace system used in the plant's processing line. Under normal operation, sections of the plant are kept at high temperatures, and the design allowed connection to burners whose full output could push temperatures far beyond normal maintenance conditions. Reinhard, a 56-year-old longtime SAG employee, and an unnamed 49-year-old temporary worker made their way into that cavity. They were not alone in responsibility for the plant's machinery that morning. A furnace operator in a separate control area was charged with managing the system, typically from a remote interface that controlled heating cycles. The sequence that followed has been reconstructed from investigation reports and trial records. The men entered to inspect the plate, sliding doors at the chamber closed and latched. In the control room, the operator initiated a heating cycle that brought the connected furnace up to its operating temperatures. Temperature figures are central to understanding what happened. The preheating chamber ordinarily reached about 752 degrees Celsius, 400 degrees C, in routine conditions. When the chamber was connected to the adjacent furnace and its burners, temperatures could escalate to roughly 1,472 degrees or 800 degrees Celsius. What engineers describe as a rapid heat-up, in a space with doors sealed and no immediate escape route, left virtually no time for survival. Minutes later, those inside could no longer be rescued. Their remains were recovered hours after the heating cycle had been stopped. Investigators focused on a familiar set of issues: procedures that should have prevented the furnace from being started while personnel were inside, visible warnings, and physical lockout-tagout mechanisms that were absent or not used, and communication failures between maintenance crews and the control room operator. The official reconstruction found that the required lockout and tagout and visible warnings were not implemented by those entering the chamber. During subsequent legal proceedings, courts examined both individual actions and institutional responsibilities. The trial records show that the company and employees were found not guilty, with the ruling emphasizing the victim's failure to follow required safety procedures. That ruling and its reasoning remains controversial for many observers because it frames the event largely as a violation of procedure by the workers who entered, rather than an organizational shortcoming in training, signage, or systemic enforcement. Pause here to reflect. The scene at SAG was not a sudden, inexplicable failure of technology. The furnace did what it was designed to do: generate heat. What failed was the human-system interface, the mechanisms and habits intended to assure that heat never met an occupied space. Lockout-tagout exists precisely to prevent activation of energy sources while people are exposed. When that barrier is absent or bypassed, a machine's proper functioning becomes lethal. An operator initiating a routine cycle, uninformed that maintenance personnel are inside, illustrates the brittle edge where procedural lapse meets engineering power. In July 1986, in a small finishing plant operated by Evernu Metal Products, a different technology and a different risk factor produced an equally devastating result. The plant used trichloroethylene, commonly abbreviated TCE, as a solvent in an industrial degreasing tank. TCE is effective for cleaning metal parts precisely because it evaporates and carries contaminants away, but when heated, it presents a severe inhalation hazard. On the day in question, work was underway on a Saturday by a 3-person crew engaged in cleaning operations. The plant's practices, as later described by investigators, were not governed by formal, written procedures. Training was informal and based on worksite custom. The tank involved had been heated to very high temperatures for degreasing. Investigators determined that the solvent had not been fully drained and that the tank itself remained extremely hot, approximately 1,000 degrees Celsius, about 538 degrees at times, conditions that produce dense, heavy solvents vapors. Trichloroethylene vapors, when concentrated in a confined space, can incapacitate a person in minutes and quickly lead to loss of consciousness, respiratory failure, and death. On that day, 3 employees, identified in reports as Arnaldo, Thomas, and James, entered the tank area without an adequate ladder, without ventilation designed for the confined space, and without respiratory protective equipment appropriate for TCE exposure. All 3 were exposed to lethal concentrations of vapor and later died. The immediate aftermath compounded the human toll. 18 police officers and 9 emergency medical personnel who attempted rescue or were exposed during response operations suffered injuries or exposure-related effects. Those who entered unaware of the vapor hazard were themselves incapacitated, creating a cascade of additional victims. This pattern, initial victims followed by injured responders, is a grim but well-documented risk in confined space incidents where hazardous atmospheres are not identified or controlled. NIOSH carried out an in-depth investigation, and its findings were unequivocal about preventability. The agency reported a pervasive lack of written procedures, absence of formal training, lack of mechanical ventilation, and absence of respiratory protection appropriate to the hazard. NIOSH concluded that the deaths were preventable and directly tied to systemic failures. The company's reliance on informal on-the-job knowledge, the failure to recognize a confined space hazard, and the absence of engineering and administrative controls that would have kept workers and rescuers safe. Reflecting on the Evernu tragedy, the technical details are not abstract. Solvent vapors are invisible, heavier than air in many cases, and can settle in low points of tanks and pits, producing pockets of lethal atmosphere that routine sight and smell cannot reliably detect before incapacitation. Confined space regulations and best practices, permit systems, gas monitoring, mechanical ventilation, and the use of retrieval systems and breathing apparatus exist precisely because hazard recognition is not intuitive. When organizations skip these protective layers for the sake of speed, convenience, or because risks have not been formally acknowledged, the outcome can be catastrophic, not just for the initial workers, but for the community of responders who rush in to help. Our third block moves from fluids and furnaces to machines that were meant to reduce human exposure to danger, industrial robots. In the late 1970s and early 1980s, factories accelerated adoption of robotic automation, machines that could perform repetitive tasks like welding, material handling, and assembly far faster and without fatigue. Robots are not sentient. They are controlled by logic and programs, and their safety depends on physical guards, interlocks, emergency stops, and human procedures. But as adoption outpaced regulation and training, tragic failures occurred. 2 fatalities separated by only a few years illustrate both the novelty of the hazard and the recurring themes of human-system mismatch. On January 25, 1979, in Flat Rock, Michigan, Robert Williams was killed in an incident involving a massive parts handling system. The system, designed to move and store heavy components, misclassified Williams as a load and crushed him. Reports indicate the machine continued operating for approximately 30 minutes after the event before being stopped. Legal proceedings that followed resulted in a civil award of $15 million. The case highlighted serious deficiencies in guarding, detection, and emergency intervention. Robert Williams' death is an early documented U.S. case that complicates later claims of first robot fatalities elsewhere in the world. On July 4, 1981, Kenji Urada, a maintenance worker employed at Kawasaki Heavy Industries, was killed in Japan while carrying out maintenance tasks around a robotic cell. According to investigation records, Urada entered the protected area by climbing over a safety fence and bypassed an interlock, allowing the manipulator to energize while he was within its reach. Co-workers present were unfamiliar with the robot's controls and unable to quickly stop it. The robot's motion struck and killed him. Press coverage at the time and in subsequent years sometimes described Urada as the first person killed by a robot. But this description ignores earlier documented fatalities such as Robert Williams. The correct account requires nuance. Robot-related deaths were rare but did occur in multiple countries as automation spread, and claims of being first must be checked against records. What do these robot cases share with the SAG and Evernu incidents? Again, the lethal combination is not the presence of advanced machinery, but gaps in protective layers, fencing and interlocks that were bypassed or non-functional, inadequate training for maintenance personnel and nearby workers, emergency stop mechanisms that were absent, inaccessible, or unknown to employees, and organizational assumptions that physical barriers alone would suffice, where behavioral and procedural factors mattered as much. In some cases, plant cultures tacitly encouraged shortcutting safety protocols to maintain production. In others, the rapid pace of new technology meant regulations, standards, and training lagged behind deployment. Industry and regulators eventually responded. Standards for machine guarding and for control of hazardous energy, commonly expressed as lockout, tagout, were strengthened and enforced more rigorously. Employers adopted redundant systems, physical guards combined with presence-sensing devices, multiple interlocks, clearer signage, and emergency stop procedures that were straightforward and taught regularly. Training curricula expanded to include predictable maintenance routines and worst-case scenarios. Yet even with these changes, history shows that human error, informal practices, and organizational blind spots can undo engineering protections. Between these three case studies, there are clear repeating patterns. First, established safety systems, procedures, interlocks, lockout, tagout, and engineering controls lose their protective power when they are not consistently used, not enforced, or not fit for the operational context. At SAG, a heating system performed as designed when activated. What failed was ensuring nobody was in the danger zone. At Evernu, a solvent vapor hazard was treated as a routine procedure, instead of a confined space hazard requiring permits, monitoring, and ventilation. With robots, physical guards and access controls failed when workers bypassed them, or when training did not prepare employees for how and when to stop a machine in an emergency. Second, informal culture matters. Across all three incidents, practices learned informally on the job replaced formal training and written procedures. Informal knowledge may be effective when conditions are stable and hazards are well known, but it becomes fragile when systems or personnel change. Temporary workers, contractors, and maintenance crews are especially vulnerable in environments where safety knowledge is implicit rather than codified. Third, rescue and response amplify tragedy. In Evernu's case, emergency responders and bystanders became victims themselves because they did not have immediate awareness of the hazard and lacked appropriate equipment. In confined space incidents and toxic atmospheres, unplanned rescues are frequently the reason additional lives are lost. Planning for rescue, having retrieval equipment, trained entrance in supplied air respirators, and clear communication must be as much a part of hazard control as preventing the initial exposure. Fourth, technology is neutral in the face of institutional choices. Robots removed workers from repetitive risk, but introduced new exposure during maintenance and programming. Furnaces work as physics dictates. Solvents evaporate as their chemical properties require. The question is not whether technology is inherently safe, but how well organizations design systems that anticipate human behavior, enforce procedures, and prepare for failure modes. Now to the horrible truth we promised to unveil. It is not that machines became malicious, or that a single person's error explains every disaster. The horrible truth is institutional and cumulative. Multiple layers of protection, engineering, administrative, training, culture, and regulation, are required to keep people safe. When organizations accept shortcuts, tolerate informal practices, fail to update training to match technological changes, or neglect written procedures and supervision, the absolute energy contained in industrial systems, whether heat, chemical vapor, or mechanical force, operates without human mitigation. The outcome is often irreversible. What concrete lessons emerge from these tragedies? They are not revolutionary. They are actionable and practical. First, lockout-tagout must be unequivocal. Any work that places a person in proximity to energy sources, electrical, thermal, mechanical, or chemical, requires a documented isolation procedure that is visible, verifiable, and enforced. The presence of an isolation tag and a physical lock, combined with a system-level interlock that prevents remote activation, reduces the chance of a fatal mistimed start. Second, confined spaces demand respect and planning. Written permits, atmospheric monitoring, continuous ventilation, rescue plans, and trained entrance are the minimum. Respiratory protection is not an afterthought. Under conditions of heated solvent vapors such as TCE, respirators and supplied air systems can be life-saving. Rescue must be planned to avoid converting rescuers into victims. Third, training must be formal and recurrent, and it must include contractors and temporary workers. Working knowledge that exists only in an experienced employee's head disappears when that person is not present. Written procedures and visible checklists reduce reliance on memory and assumption. Fourth, machine guarding and automation controls require layered defenses. Fences and interlocks are important. Presence-sensing devices, redundant emergency stops, clear labeling, and lockout-tagout for robotic cells are equally critical. Training must include how to isolate and power down systems unexpectedly and how to respond when someone is found to be inside a guarded area. Fifth, emergency preparedness and medical response planning must recognize the specific hazards of the workplace. Responders must be equipped and briefed on likely atmospheres in confined spaces, on the potential for residual heat, and on the difficulty of extricating victims from powered systems, elements that change rescue tactics and equipment selection. Sixth, organizational culture and accountability must align. Safety cannot be a peripheral check-the-box activity. Regular audits, independent safety reviews, and transparent incident reporting are necessary. Investigations should identify root causes beyond immediate operator error, because focusing solely on individual fault can obscure systemic opportunities for prevention. The aftermath of these incidents did produce reforms. NIOSH's findings from Evernu influenced guidance and regulations around confined space entry and solvent use. The robot fatalities prompted industry-wide adoption of more comprehensive guarding systems, clearer standards for maintenance access, and reinforcement of lockout-tagout in automated environments. Saggi's tragedy led to intense discussion in Europe about procedural enforcement and the adequacy of worker protections in high-temperature processing plants. But reforms are rarely absolute. They must be monitored, applied, and refreshed as technology and workforce compositions shift. We must also speak candidly about justice and memory. Courts and investigators pursue different questions. Courts determine legal responsibility based on the evidence and legal standards before them. Investigators aim to reconstruct events to prevent recurrence. In the SAG case, the verdict found the victims had not followed required safety procedures. In Evernu, the NIOSH report placed clear responsibility on systemic failures. Legal outcomes do not always equate to moral clarity, and they do not restore lives lost. Remembering the names, Reinhard, Arnaldo, Thomas, James, Kenji Urada, Robert Williams, and the responders who were harmed is part of honoring the human cost and an essential motivator for prevention. There are also important nuances the public must not lose. Headlines that simplify these tragedies, saying, for instance, that a robot killed its first worker, erase context and history. Robert Williams' 1979 death predates some later claims of firsts. Acknowledging the correct chronology does not diminish the shock of any single event, but it prevents myths from crowding out facts. Similarly, when investigations note that workers failed to follow procedures, that observation should trigger questions about why the procedures were not followed. Were they absent, ambiguous, impractical, poorly communicated, or culturally deprioritized? If you work in industry, supervise teams, design systems, or participate in emergency response, how should you act on what you've heard? Start with audit and verification. Walk through the workplace with fresh eyes. Where could someone enter a hazard without being detected? Where are temporary workers not included in training? Where do procedures exist only in the supervisor's memory? Make sure lockout tagout is not an abstract policy, but a practiced routine. Require permits for confined spaces and run drills that include recovery of a downed employee without turning rescuers into casualties. For automated cells, require redundancy, physical barriers, plus presence sensing devices, accessible emergency stops, and documented isolation procedures that maintenance crews must follow. Regulators and industry bodies must continue updating standards to reflect evolving technologies and workforce realities. Emerging automation, remote diagnostics, and new chemical processes demand anticipatory standards rather than reactive ones. Training curricula should include scenarios, near-miss case studies, and focused exercises for those who will be performing maintenance and rescue. And investigators and courts should aim to present findings that both assign responsibility where it is due and illuminate systemic corrections that will prevent recurrence. We close where we began, confronting a horrible truth that is not an indictment of technology, but of the fragile interface between human systems and engineered power. Furnaces will heat, solvents will vaporize, robots will move with programmed force. Those facts are industrial constants. What we can change and must change are the layers that keep those constants from reaching human bodies. Rigorous procedures, enforced lockout to tagout, formal training, engineered safeguards, thoughtful rescue planning, and a culture that privileges safety over short-term convenience. If this video moved you, if you were shocked or saddened by these accounts, consider subscribing so we can continue to explore workplace safety and institutional lessons together. If you or someone you know has a workplace safety story that should be investigated, please submit it through the link in the description or leave a comment below. We review submissions carefully and treat personal accounts with respect and discretion. These are not abstract lessons. Each number, each temperature, each date, each name represents a life and a family. Remember them and let their stories drive concrete change where you live and work. Thank you for watching, and take care.